Hello students, welcome back. Previously we defined kernel. Let phi be homomorphism from a group G to another group G prime, then the preimage of the identity element E prime of G prime is called a kernel. In other words, an element of G belongs to kernel means the function value of that element is E prime. And then we proved that the kernel is always a subgroup of G. And the proof was actually a one-liner as a matter of fact, because the kernel is a preimage of the trivial subgroup of G prime. And preimages always preserves all the subgroup structure. So this image, by the way. And consequently, it's a subgroup. But then again, as an exercise, we went through the direct proof as well. Okay, so far so good. Let's go to the next topic. A homomorphism is one-to-one if and only if the kernel is trivial. And this is the smallest possible kernel. The kernel cannot be the empty set because at least the identity must exist in a group, and that identity must go to the other identity. E must go to E prime. Remember, homomorphisms preserve the identity and inverse, and also the group operation. So this is the smallest possible kernel. The question is there any other element? Well, it turns out phi is one-to-one if and only if kernel is trivial, and this is a biconditional statement, so we have to prove both direction, forward direction and backward direction. We have two proofs, rather two steps of proofs, two parts of the proofs. Let's do the easy one first. Assuming G is one-to-one, as I highlighted in green, let's prove that the kernel is trivial, highlighting in blue. So what do you mean by kernel is trivial? That means every element of kernel, no matter what I select, should be equal to E. You see, you don't have to consider the other way around. E always belongs to kernel. Remember, phi takes E to E prime all the time, so we don't have to consider that. It's the other way around we have to consider. If there's anything in the kernel, it should be E. In other words, that's what you have to prove. Make sense? That's what you have to prove. Select anything from kernel, and X is E. That's how you prove this conclusion. Now, how do you prove that? Well, in the technical part, we'll have to use this green somewhere, somehow. So that's the strategy. Make sense? But then again, something belongs to kernel, that's a bit cumbersome to work with. What's the better way? As we practiced a couple of times already in the previous video, it's going to be better if I reduce that like this. This one as so this one here, X belongs to kernel, means phi of X is E prime. Those are the same. Now somehow connect this and that using phi is one-to-one. Somehow. How do you do that? Any idea? How do you apply this green somewhere here? Any idea? No? Giving up? Well, here we go. That's the key idea. That's where I use this green. Phi is one-to-one. let's see. X belongs to kernel means phi of x is e prime, so far so good. But then again, phi of e is also e prime. And phi is 1 to 1, so x and e have to be the same. You see, phi of x and phi of e share the same output. So the input must be the same as well, because phi is 1 to 1. So we get our conclusion, x is equal to e. So rewriting this x belongs to kernel into phi of x is e prime, that's straightforward. That's from the definition of the kernel, and we already went through some exercises associated to that. That should be easy by now. And the key point is, another observation, phi of e is also equal to e prime, and there you can use this green condition. Phi is 1 to 1, and the conclusion follows. Okay, that was a proof. Now let's go to step 2, and this is going to be a bit more challenging. How do I write this green? Phi is 1 to 1 map. What do we have to prove in order to establish phi is a 1 to 1 map? Any idea? If you have different elements, then they will have to go to different elements. That's the idea of 1 to 1. But different means not equal. If you have too many not equal, that means too many negations, too complicated. Better to take the counterpositive and rewrite like this. Same input follows from same output. Make sense? Function values are the same, then they must have come from the same input. Same input follows from same output. Same output, then same input follows. So different inputs will give you different output, and then take counterpositive. Same output will give you same input. Yeah, I think that's better expression. So different inputs will give you different output versus counterpositive. Same output gives you same input. And then at some point you'll have to use the fact that kernel is just trivially E. How do you do that? How do I utilize kernel one way or the other? Well, we have to get E involved one way or the other, you see? On the one hand, kernel is just trivial E. On the other hand, kernel is all about E prime, so you have to use the identity one way or the other. How do I do that? Well, here's my suggestion. Flip this to the other side. And then this one too. Flip this to the other side. So this one here, phi of x1 is equal to phi of x2 versus phi of x1 times inverse of phi of x2 is e prime. This one here and that one there are the same. Does it make sense? This one here and that one here are the same. So if you just multiply phi inverse to both the left hand side and right hand side here, and then here I'm going to get cancellation to this e prime. So in the end we get what we want. The same thing goes here. Multiply x3 inverse to both this one and that one, and then here we have a cancellation, we have just e. Now can you connect this one and that one way or the other? Using the property of homomorphism, well, inverse will go inside the parentheses, and then we can combine these two together as x1, x2 inverse. x1, x2 inverse comes right here. Looks like that's possible. Here we go. We got up to here, so we don't need that anymore. And then let's use the property of phi, put inverse in there, and then put together phi of x1, x2 inverse. Inverse inside, phi of x1, x2 inverse is E prime. Does it help? We did get this expression here, so yeah, we have somewhere, but not quite yet. So how do I utilize this blue? Well, let's make this observation. Phi of this element is E prime, which means this element belongs to the kernel. This thing belongs to the kernel. But then again, kernel is just E. So if this element belongs to the singleton, then this thing must be equal to E. So phi of x1 and phi of x2 are the same. Through this process, we're down to phi of x1 and x2 inverse is E prime. Yeah, okay, all these are repeat to all those here. And then x1, x2 inverse belongs to the kernel, but kernel is just E. So x1, x2 inverse is E, and bingo, x1 is equal to x2, that follows. Cool. This whole thing is a bit hard to follow. So let's do one more. Okay. And then okay, let's conclude like this. So start from here. Function values are the same. Flip one to the other side. And right hand side E prime. Slip this inverse inside because that's what homomorphism does. And then put these together and then get x1, x2 inverse because that's what homomorphism does. And right hand side E prime. Consequently, x1, x2 inverse belongs to the kernel because that's what kernel does. But then again, this kernel is just a singleton E. So x1, x2 inverse is equal to E. In other words, x1 and x2 are the same. And put everything together, we get this kind of lengthy explanation. Lengthy and concise at the same time, but I don't know whether you can follow all that. Let's keep it simpler. And by the way, the forward direction was much easier. Okay, that concludes the proof. Homomorphism is one-to-one if and only if the kernel is trivial. By the way, similar argument applies for vector spaces and linear maps. A linear map is one-to-one if and only if its kernel is just trivially zero. Same argument applies.